Hello friends, in this session we are going to see about chemical energy storage system. Along with this we are going to see about 3D solar cells. First of all, considering the chemical energy storage system, in this we are going to see about hydrogen fuel cells alone. See, normal chemical storage system stores energy in the form of chemical which are in the form of gases, liquid or solid, and they can release energy through any chemical reaction process. Coming to the hydrogen fuel cell, this is the diagram of a hydrogen fuel cell. If you see here, hydrogen is taken as an input to this device. The oxygen is combined with hydrogen, it gives the H2O, which gives water as the output. During this chemical reaction, suitable amount of energy is generated outside, and this is being regulated with the help of the charge controllers, and it is stored in a conventional battery and it is given to the external load. Hydrogen is a clean fuel that when consumed in a fuel cell it produces only water. See, this hydrogen can be produced from variety of domestic resources, as we already know: natural gas, nuclear power, biomass or renewable power like solar and wind. These qualities make it more attractive for an alternative energy generation, which is also mainly suitable for transportation and normal electrical generation application. Some of the domestic applications are, it may be used in electrical vehicles, in household applications and portable power devices. This chemical reaction as shown in this diagram are by the redox reaction, where you will be having oxidation and reduction, which is called as the redox reaction. See, fuel cells are different from the conventional batteries because it requires continuous source of fuel and oxygen to sustain in a chemical reaction. But in a conventional battery we will be having chemical reaction usually coming from the metals and their ions that are commonly present in the battery. But in the case of fuel cells, we require the fuel and the oxygen continuously. Also, the fuel cells can produce electricity continuously as long as the fuel and the oxygens are supplied. Even though the production is going to be complicated, but the energy density of hydrogen fuel cell will be around 120 megajoules per kilogram, which is 3 times more greater than the energy produced from diesel or gasoline. See, in terms of electrical, the energy density of the hydrogen is around 33.6 kilowatt hour. In turn, in the case of diesel, it will be only 12 to 14 kilowatt hour per kg. This is about the introduction of hydrogen fuel cell. See, if you look at the plot given at the right hand side, see here you will be having the specific power, and we are having the specific energy in the y-axis. The most of the commonly used energy storage systems are given here. See, mainly see here in fuel cells the specific energy is low when compared to other type of energy storages. Also, if you see here, the combustion engine gas turbine has both specific power as well as specific energy. Because of this reason, mostly we are using this type of engines or gas turbines to produce energy or to store energy. Since we are going to other type of energy storage systems, at present we are not considering about this. Let us see other type of energy storage systems. Here we will be having normal electrolytic capacitors, where the specific power is going to be very high, but the specific energy is less when compared to the other type of systems. Also, here we have supercapacitors, which is more reasonable. Also, we have a flywheel, which is economical when they are used in a large scale. If you see, lead acid batteries are commonly used since their specific power is slightly less, but they can produce specific energy. Then we move on to nickel cadmium batteries. Because of the improvement in technology, we move to nickel cadmium batteries. When compared to lead acid as well as nickel cadmium, we have lithium ion batteries. If you see here, it can give specific power. Also, it can give reasonable specific energy. So in most of the applications nowadays for energy storage systems we prefer lithium ion batteries. This is the only reason we are preferring lithium ion batteries. Otherwise we will go for flywheel mechanism. Since flywheel mechanism is more complicated in construction, also it is more costlier when it is done in a lower scale. So we are using lithium ion batteries. Now we are going to see about solar based renewable energy system. The main thing is we are going to see about 3D cells. So here the 3-dimensional solar cells mainly capture most of the light that is incidented on them, and it could boost the conventional photovoltaic panel efficiency by with the same the reduced size, weight and mechanical complexity. If you see, it will be in the form of a tower like structure where solar panels are arranged in such a way that most of the lights are falling on them, so that the efficiency may get increased. Mainly these type of cells are find their uses on this is more complicated. 3 boost, you see, it will be in the form of a tower like structure where solar panels are arranged in such a way that most of the lights are falling on them, so that the efficiency may get increased. Mainly these type of cells are find their applications by powering the spacecraft. Also further this efficiency can be increased by giving a photovoltaic coating material over them. They can be used for a very broad range of applications. The research is actually sponsored by Air Force Office of Scientific Research, but still now it has not been implemented because the pattern is actually currently pending. If you see the right hand side, we have the actual structure of a 3D cell. We have a glass plate. As we already know about the conventional solar system, we have a glass plate, and we have a N-type material and P-type material. When the solar cells, when the photons hit the solar panels, there is a detach of electrons, there is a flow of electrons from the plate. When they are connected to the external load, they can power them. See, this is taken as the load from the solar panel. Here this is the actual structure that has been cells. We already know about the conventional solar system. We have a glass plate, and we have a N-type material and P-type material. When the solar cells, when the photons hit the solar panels, there is a detach of electrons, there is a flow of electrons from the plate. When they are connected to the external load, they can power them. See, this is taken as the load from the solar panel. Here this is the actual structure that has been developed, can mainly capture most of the sunlight that is incident on them. Even though it does not require sun must be at the top of the solar panel as in the conventional panel. As the sun travels from east to west, it can extract power at any direction. This is the cross section view of the 3D solar cell. The tower structure can trap and absorb light receiving from various different angles, as we shown here. So this could allow the spacecraft without any mechanical system to track the sun. Normally we will use solar sun tracking system, so we never require any mechanical system to track the sun within this setup. So this may improve reliability, but also it reduces weight and complexity of the system. In a 3D cell, we have a carbon nanotube arrays which serves both the support as well as it can serve as a conductor connecting the photovoltaic material to the silicon wafer. But the researchers are now trying to make this photovoltaic cell with the help of cadmium, since we are familiar with the cadmium already and in battery technologies. So they are working on the cadmium material. However, a broad range of materials can be used to increase the performance of the system. So in near future, these type of cell arrangements could replace the existing solar panel structure. See, the fabrication of the cells begin with silicon wafer. which can also serves the bottom junction of a solar panel. Researchers first coat this silicon wafer with a thin layer of iron using a photolithographic process. This is a photolithographic process where the wide variety of patterns are created. Then these patterns are placed in a furnace which is heated up to 780 degrees centigrade. Later, hydrocarbon gases are then passed into the furnace where the carbon and hydrogen are separated. This process is known as chemical vapor deposition. So the carbon grows array of multi-vapor carbon nanotubes on the top of the iron pattern. This is how they are producing this. You see here in recent years they are implementing this type of 3D cells in the structural buildings so that we can get maximum amount of power generated from the solar cell. Thank you. We will see in the next session. Hello friends, in today's session we are going to see about electrical and mechanical energy storage systems. First of all, we will see electrical energy storage systems. See, in this type, it stores the electrons in electrostatic field between the two electrodes. Even though the energy capacity is limited in electrical storage system, but the reaction time is going to be very fast. First of all, we will see about the superconducting magnet energy storage system. See, this is the schematic diagram of SMES. See, it consists of a chamber inside which we will be having a coil surrounded by a liquid nitrogen or helium gas. This is in turn connected by a cryogenic refrigerator, which is in turn have a storage of helium and nitrogen. With the help of this pump, this helium or nitrogen is sent to this chamber. Initially, with the help of DC power, this coil is energized, and with the help of the proper converters, this stored energy can again be given to the external circuit. Actually, SMES stores energy in the magnetic field created by the flow of direct current in the superconducting coil. This coil is the superconducting coil where energy is stored in the as a magnetic field. This liquid helium or nitrogen are cryogenically cooled to a temperature below the superconducting critical temperature. As we already saw, this device has three major parts. One is the superconducting coil, second one is the power conditioning system. Actually, here we are not showing the power conditioning system, but actually this will be attached with this. Also, we will be having a cryogenic refrigerator. Along with this, we have a pump system arrangement. Once the superconducting coil is charged, this current is not decayed, and it will store energy as a magnetic field inside this container. The stored energy can be released back to the network by discharging the coil. Actually, this power conditioning unit, we have a PCU here attached to this device. This power conditioning system uses inverter and rectifiers to transform alternative current to direct current and again back to alternative current. The energy loss of this power conditioning unit will be around 2 to 3% of the total energy, which is going to be very negligible. When compared to other electrical energy storage system, this SMES losses are very minimal. Also, the overall efficiency of the system will be greater than 95%. So, this electrical energy storage system, that is SMES, is widely used. Then comes the supercapacitor. Supercapacitors broadly divided into three types. One is electrostatic double layer capacitor, electrochemical pseudo capacitor, and the third one is the hybrid capacitor. We will see some brief about supercapacitors. Supercapacitors are also called as ultra capacitors. As the name indicates, it has high capacity when compared to the ordinary ultraelectric capacitors. Also, it can store high capacity but with a lower voltage limit. So supercapacitors are in between ordinary alternating capacitor and rechargeable batteries. Right hand side shows the diagram of the supercapacitor. The left hand side we will be having cations, and right hand side we will be having anions separated by a electrolytic medium. From both ends of the cation and anion chamber, we will be taking the current collector, which is sent to the external circuit. Actually, supercapacitor stores 10 to 100 times more energy when compared to the ordinary alternating capacitors, and it can accept or it can deliver energy at a faster rate when compared to the normal batteries. Also, supercapacitor, the number of charging and discharge cycles are more when compared to the batteries. As we already saw, if you see this diagram number B, we have two electrodes. We will be having two electrodes, and you will be having a ionic conductivity between these two electrodes. You will be having ions, unlike other type of capacitors. We will be having ions here. We will be having a dielectric medium formed in between this. For example, it may be MnO2 or any conducting polymer. Now we will see about mechanical energy storage systems. See, mechanical energy storage combines several type of storage principles. For example, energy of the water can be stored behind a dam in a hydropower storage system, and in the case of compressed air energy storage system, we will consider volume and pressure of the air as the storage element. Mainly, mechanical energy storage systems are used for grid connected applications. The first one is the compressed air energy storage, which is shortly called as CAES. Is a way of storing energy with the help of compressed air. At the utility scale, the energy generated during the periods of low demand can be released during the peak load period. So here, during the low demand time, this compressed air is stored, and during the peak load period, the stored compressed air is utilized to meet the demand. The right hand side shows the diagrammatic view of compressed air energy storage system. In this, if you see, with the help of a motor, the internal the atmospheric air is taken inside. Also, this motor is driven by the existing power supply at the low demand condition. So it takes the air and it compresses, and it is being stored here. When the demand increases, or when during the peak demand, the compressed air is then released and it is sent to the turbine via the recapturator, and the turbine is made to rotate. When the turbine is coupled with the generator produces energy. Mainly, this type of systems are integrated with the renewable energy systems such as photovoltaic system or fluctuating wind energy systems. Mainly, this CAES design is the major challenge is the management of thermal energy, because of the compressed air, the temperature gradually increases, which may reduce the overall operation efficiency of the system. This diagram shows the clear picture of this. Again, the power is given to the grid connector system during the peak load condition. When compared to the traditional battery system, this stores energy for a longer period of time, and it can be utilized whenever required. Then comes the flywheel mechanism, which is one of the very important type of mechanical energy storage system. Actually, this flywheel energy storage works on accelerating and rotor. See here, in this diagram, we will be having a motor or a generator set, which is an induction machine. Along the shaft of this induction machine, we will be having a flywheel rotor, which is maintained nearer to a vacuum state, which is maintained in a vacuum container at a very low pressure. As this rotor rotates, this flywheel will also rotate, and it can store the energy in the system as rotational energy. When energy is extracted from the system, this flywheel speed reduces. The speed of the flywheel reduces when the energy is extracted, and it can store energy when the speed is increased in this chamber. At present, we are storing this energy with the help of the normal conventional electricity, where suitable converters are used to rotate the induction machine. Also, again, this rotation machine to decelerate, to extract the power, again suitable power converters and controllers are used, so that the power is again generated or given to the grid system. Now mechanical energy storage are also being developed. Since we are using more amount of power converters here, mechanical energy storage are also being developed in recent years. When in an advanced flywheel energy storage system, the rotors are made up of high strength carbon fibers composites, and it can spin up to an RPM of 20,000 to 50,000. When the rotor spins at a speed of 20,000 to 50,000 RPM, the energy capacity that it can hold is much more greater when compared to the other type of mechanical energy storage system. Then comes the liquid air energy storage. It is also mainly used in grid connected system. Here, the liquid energy storage is sometimes referred to as cryogenic energy storage. The word cryogenic is nothing but it is the production of very low temperature. It is a production of very low temperature. See, at this low temperature, we are storing the liquid air or liquid nitrogen. In turn, that can be converted into energy. Typically, this type of technology is used in a large scale storage of electricity, that is mainly grid connected system. This is the block diagram of an liquid air energy storage system. So in this, if you see, we will be having a liquid storage tank along with the cryogenic pump. See, air from the atmosphere has been taken and it is compressed and it is stored in the energy tank, or the nitrogen is stored in the form of liquid in this storage tank at a temperature of nearly, or the nitrogen is stored in the form of liquid in this storage tank. at a temperature of nearly minus 195 degree centigrade. This liquid air or nitrogen, it will be in the form of 1,000th of the volume of the gas. So it can be kept for a longer time in the large vacuum container at the atmospheric pressure. At the time of high demand of electricity, this liquid air is pumped at high pressure to the heat exchanger and then it is sent to the boiler. In this diagram you can see here, with the help of the cryogenic pump, it is been sent to the heat exchanger. As the high pressure steam hits the turbine, as we already know, this generator which is coupled with the turbine rotates and power is generated to the grid at the peak load demand. This is about the energy storage, mechanical energy storage system. Then comes the pumped hydro storage. See, this is the diagram of the pumped hydro storage system. See, if you see here, we will be having the existing hydroelectric plant here. We have a inlet pipe which is coming from the downstream lake or pond. See, with the help of a small amount of pump set up here, and during the light load condition, this water in the downstream is sent to the reservoir. It is stored in the reservoir, and when there is a peak load demand, from this reservoir, the stored energy is being converted into electrical energy by the same principle of hydroelectric power plant. Normally, when these dams are filled with natural rainfall conditions, then this part will act as a conventional hydroelectric power plant. See, the major drawback of this is we required with the initial investment of arrangement of this setup is going to be very high, but the operating cost, see, this water pumping system works and only at the low demand condition where the electricity price is less. But during the high demand condition, the price of the electricity will be more, so that the overall operating cost will be reasonable. This type of pumped hydro storage systems also will be useful for grid connected systems. This is about the mechanical energy storage system. Thank you. We will see in the next session.